Right now we will introduce our architecture of our system. So we can see our system include two components. On the right side, this is the database we want to tune, and so on the target database server, we have the database monitor, which running on the target database server. It's used to collect the internal database metrics from the target database, and those metrics will pass to the tuning server. The tuning server will run a machine learning method to finally get a recommendation configuration for the database. So for the tuning process, we split into two phases. One is training phases, another one is recommendation phases. For the training phases, there are four steps. One is observation. Observation phases is we use the benchmark tools to generate some specific classic workloads such as a TPCC. Maybe we use a TPCC workload create with 200 warehouse and 15 users. Those workloads go through the target database, and our monitor will starting several observation phases with the same workload but different kind of configurations. So after the first observation phases, we can get several metrics for different observation periods. So in the second steps, which we call the metric selection, is so after the first observation, we can get some metrics which we show you on the motivation part. So in the second metric selection phases, our purpose is reduce the size of the matrix which we get from the observation part. So we use two methods to achieve this purpose. One is a factor analysis. Another one is a machine learning method called k-means. So this factor analysis method will reduce to remove the redundant matrix and to reduce the size of the matrix. And the k-means is a clustering method, which means we will based on the workload feature, we will group the existing matrix into several groups. So here's the problem when we're using those machine learning methods into the database tuning. Since the k-means is a very classic clustering method, but they can group the data into several groups, but they cannot decide how many groups we group the matrix here. As we see, if we're running a k-means, it will generate k from 1 to 20, which means they will group the matrix into one group, into two groups, into three groups, and until into maybe 19, 20 groups. But the problem we meet here is how to decide which k we should choose. So here we use we propose an interpretable method to help us to define which k we should choose. So this is this word is from the POSIX official website. From the system point of view, they split some of the metrics into 6 categories, and we assume those metrics in the same category have the high correlated relationships. So our proposed algorithm, the key idea of the purpose of the algorithm is we try to we try different kind of a key, and we try to make the clustering generated by k-means has a more matrix into the same system level groups, and the details we will show you in the paper. So let's come back to the architecture workflow picture. So in the matrix selection phases, we can see we have two tasks. One is reduce the size of the redundant matrix into k groups of the matrix, and we just use the one matrix in each groups to stand for the whole groups. So this process can help us use a much less matrix to stand for the workload. Meanwhile, we propose characteristic tables, which it looks like this one. So the characteristic tables will record the future feature of the workload by for instance, we reduce one of the keynote, then we capture the different different metrics, whether it's increase or decrease, and this is we so-called the characteristics table, which will record the feature of the workload. So in the second step, now we get a compressed characteristic table and selected matrix by k-means, and this step is for get the feature of the workload. So in the second step, and now we have the keynote configuration and the different selected matrix, and we put these two into to generate the most important keynote configuration items for this workload. So here we use a lasso. So here's a demo we show. So this is with the input of this program is observation test result, and here is a FA result. So here we can see this is a lasso result. The result of the lasso is we using the feature of the workload and the configuration to generate what's the top important keynote configuration to optimize the current workload. Here we have because for optimize workload, we have a target. We will first set a target. For instance, here we say the throughput of the database as a target. So those keynote are ranked for highly important for improve the throughput. So after the ranked keynote phases, we have right now we have the characteristic table and which can represent the feature of the workload, and right now we have the ranked keynote, which is important for improve the target matrix performance. So we put this two, we use this two to generate the best keynote configuration, which means, for instance, we choose the most important keynote from the result of the lasso, and we use characteristics table to see whether to improve the throughput, we should increase this item or decrease the value of this item. So after that, we can generate the best keynote configuration for the training dataset. And in our paper, we show that we after the best keynote configuration can improve 30% performance for the database throughput. With the detail we can show in we can see in the paper. So this is a process of the training phase. So after the training phase, there are several workload feature and compress the characteristic table and rank the keynote, and the best keynote configuration will store in the historical workload repository, which means that the AutoTune those workload as a repository. So here is the recommendation phases. Recommendation phases means when the unknown workload go to the DBMS. So what we do is, first we also doing observation. We observe the internal matrix, and which is the same as the training phase. Then we can also get the current workload characteristic data table. And the second process is we try to map the unknown workload to the historical compressed historical trained workload. We use compute the distance between the current workload characteristic table and the historic compressed characteristic table. The distance, with the minimal distance, we find the most similar workload. And meanwhile, because the best configuration for the workload are stored in the repository, we just apply the best keynote configuration to the unknown workload, and to see whether the workload performance is improved. And in our paper here, we compare we go through this process, and we can find the unknown workload is more close to a TPCC workload. So the performance the unknown workload using the recommended keynote configuration can improve roughly 25% of the performance. The detail we can show you in the paper. Okay, thank you.